Today we are looking at intraoperative nuclear imaging. To do so, we first have to discuss medical nuclear imaging. So what is that? Medical nuclear imaging is a type of functional imaging that is used to visualize how processes in a living body work. Its fundamental principle is to administer a radioactive compound and then measure the emission and where it comes from. So unlike other imaging modalities, the emission originates from within the patient's body. There are different ways to perform nuclear imaging, most of them requiring big imaging devices. A straightforward approach is having one or more big planar detectors next to the patient. With those, the gamma radiation emitted by the radioactive compound can be counted for a specific amount of time to produce a so-called scintigraph image. If you let the planar detectors now rotate around the patient and collect measurements from different directions, it is possible to reconstruct a 3D image. This is called single photon emission computed tomography, or in short, SPECT. The idea is very similar as extending X-ray imaging to X-ray computed tomography. But how does this work in hardware? A nuclear imaging device comprises several components. The most important part is the detector, which in the case of our drawing is a semiconductor crystal, here in blue, and is connected to the electrodes on either side. In front of the detector there is a collimator, which blocks all the photons not coming from a certain orientation. So suppose we have a radioactive source in front of our detector. It emits photons in all directions, but because of the collimator, only some reach the detector crystal. When a photon interacts with the detector, it is absorbed and creates a large number of electron-hole pairs. Because of a high electrical field between the electrodes, the electrons, here in yellow, travel towards the anode at the back of the detector, where they are amplified and processed by electronics. A different way of nuclear imaging is positron emission tomography, in short PET. Here, the principle of how the radiation is produced and measured is slightly different. The radioactive compound administered to the patient does not itself emit gamma photons. Instead, it emits during its decay positrons, which are the antimatter counterparts of electrons. When such a positron hits an electron, both particles annihilate and produce a pair of high-energy gamma photons, traveling in opposite directions. And this principle can be used for the detection. If two photons are detected at the same time, it is very likely that they were created in the same positron-electron annihilation. Therefore, the annihilation can be assumed to have happened somewhere along the line between these two detectors. The big advantage of this approach is that collimators are not needed, which increases the sensitivity of the system greatly. However, for the detection of annihilation events, two opposing detector plates are required. Now you have seen the most common nuclear imaging devices: scintigraphy, SPECT, and PET. Providing images for many diagnostic purposes, they have become an integral part of modern healthcare. However, the scanners are usually room-sized and offer very limited possibilities for interventions and operations. So the question is now, how can we translate the principles of nuclear imaging into the operating room? Let's look at an exemplary clinical application where nuclear imaging can improve the clinical outcome: sentinel lymph node biopsy in breast cancer. During routine checkups, a woman gets diagnosed with early-stage breast cancer. The tumor is still comparably small, maybe not even palpable yet. However, the treatment depends on the exact stage of the cancer. If it has spread to the lymphatic system, a higher dose of chemotherapy is induced, compared to a lower one when there are no metastases yet. As cancer cells in general spread through the lymphatic system, it is shown that the pathological result of the first lymph node having lymphatic drainage from the tumor is sufficient to determine the stage of the cancer. This lymph node is called the sentinel lymph node, in short SLN. They are hard to find in the operating room because they are very tiny structures and mostly do not look different than other lymph nodes, which are in close proximity. Therefore, some techniques for their mapping are essential. The standard clinical workflow is to inject a tracer near or inside the tumor. The tracer will then drain through the lymphatic system and accumulate in the sentinel lymph node. If this tracer is radioactively marked, then it is possible to image the sentinel lymph node using a standard nuclear imaging technique such as scintigraphy. These images are good to see how many lymph nodes get drainage from the tumor and determine their approximate location inside the body. However, since they do not show the anatomy in the first place, and since the images are not acquired inside the operating room in the exact same patient positioning, they cannot be used directly during surgery. Because of these limitations, surgeons use a small handheld radiation detector in the operating room instead, a so-called gamma probe. It can detect radioactivity and beeps proportionally to the number of detected gamma photons. The surgeon sweeps over the region of interest until he finds the most active site and then performs the biopsy accordingly. This approach works pretty well if the lymph nodules are well separated or if you want to take out the entire lymph node cluster. But as you can imagine, this is not always the case, so more sophisticated approaches are needed. Can we offer tomographic nuclear imaging such as SPECT in the operating room without using huge scanners? The answer is yes. For a 3D reconstruction, we only need to scan the region of interest from a sufficient amount of directions and determine not only the photon count there, but synchronously also the location of the gamma probe in space. In order to know the probe's location in space, a tracking system is needed. It comprises a pair of cameras, an infrared illumination source, and retroreflective markers. When the illumination source flashes, the markers can be easily detected in the images of the two cameras. From the different pixel positions of the markers in both images, their 3D location in space can be inferred. To track the location of the gamma probe, a so-called tracking target made out of a set of marker spheres is attached to it. The only unknown now is the spatial relationship between the tracking target and the tip of the probe that detects the photons. By inserting and rotating the probe in a precise calibrator with known geometry, all geometric unknowns of the system can be determined. In the end, accurately calibrated gamma probe and tracking system measurements are combined. While such a set of measurements may look very different from the one a standard SPECT scanner would produce, the reconstruction into a 3D volume follows the same mathematical principles. But we can even do better than this. The gamma probe we have used so far is actually only a single pixel detector. Recent advances in detector hardware development have allowed the design of relatively lightweight handheld gamma cameras. The combination of these cameras with the previous ideas of tracking the detector enable us to produce images with a much superior quality in terms of resolution and shorter acquisition times. However, a much more accurate modeling and calibration of the camera setup is necessary to fully exploit the detector's possibilities. In an exhaustive manner, a radioactive point source is positioned at different locations in a regular grid, and the counts for each of the camera's pixels is recorded. This is then used to generate a 3D probability map for each pixel, telling us where in space a detected photon could have come from. Here you see a patient with early-stage breast cancer who is about to have a sentinel lymph node biopsy performed. With a tracked gamma camera, the left axillary region is scanned. In the augmented reality view, the white cube guides the operator in scanning from a sufficient amount of directions to allow a 3D reconstruction. By using intraoperative SPECT, the sentinel lymph node of this patient could be successfully located and the biopsy performed. If you're interested in intraoperative nuclear imaging or medical imaging in general, please visit our website and come in contact with us.